main players in the field of laser interception of targets. And solid-state lasers are can be made of crystal or fibers. Chemical lasers are made of mixture of gases. I'll talk about these in a minute. Semiconductor lasers are very efficient, but they're small in power, or they have low power. Gas lasers were, in the beginning, mainly CO2 lasers were used also for interception systems. And there are liquid lasers, but these are also low power lasers. And free electron lasers, which were mainly had a boost in the Reagan time in the SDI initiative. They can be very powerful, but they're very large and static, and since then, not real development has been made. So I'll focus now on these two types of solid-state and chemical lasers. So crystal-based solid-state lasers are made of a resonator. You can see here on the left and the YAG crystal with a pump source. And the output beam from the resonator, from the oscillator, goes into an amplifier chain and is being amplified and can be amplified. So this laser operates at 1 micron wavelength, which is the natural wavelength of Nd:YAG. It's non-eye safe. It can damage the retina. So damage is a eye safety issue with these lasers. And combining 5 laser channels led to 100 kilowatt output power. This happened in 2010. Main issues of these crystal-based solid-state lasers are heat removal, because there's a lot of heat to remove. The efficiency is not too high, and the beam quality is not optimal. Fiber-based solid-state lasers are based on double-clad optical fibers, which have two waveguides, I would say. One is the inner core, where the active ions, laser ions, are embedded. And the other is the clad, the blue clad here, where the pump is guided. So the pump is guided in the blue and is slowly absorbed in the red region. And then you put 2 mirrors and you get a laser out of this. So the beam quality is excellent, M²1, depending on you can get it from the fiber because it's dictated by the waveguide. And this really came in since 2000 and now is very successful in terms of replacing lasers in different applications. So this is a laser configuration you can see here. On the bottom, you can see pump diodes, pump combiner. The pump goes into the double-clad fiber. And then you have 2 mirrors inscribed in the fiber, so high reflector and output coupling. And you have active fiber. So this is basically an oscillator, fiber oscillator. So these fiber-based solid-state lasers also operate around 1 micron, from 1030 to 1100, mainly in the 10,000 for high power, in the 1070 or 1080 wavelength regime. Non-eye safe, because this wavelength regime is still non-eye safe. And lately, beam combining of this led to 60 kilowatt systems, and there are R&D plans to get to 300 kilowatt systems. In my opinion, development of 500 kilowatt systems, it'll take at least 10 years till this can become an operational system deployed in the field. But fiber lasers are currently the leading laser-based systems for intercepting small rockets and other flying stuff. Chemical lasers are based on a reaction between 2 gases, typically a mixture of hydrogen or deuterium with fluor. And this generates excited molecules, and then you have the gain. So these gases are hazardous, and you can see here on the left, a typical scheme. You can see the gas going into the oscillator, and you have two cavity mirrors, and it's a flowing gas, so you have exhaust gas, and you have the laser beam coming out from the bottom here. So this type of lasers operates between 2.8 and 3.8 micron. So that's in the, let's say, mid-IR range, depending on the gas mixture. And it's eye safe. The beam is eye safe. It cannot penetrate the retina. This is the only laser I know of that surpassed 100 megawatt CW for short periods of time. Was the chemical lasers were very popular until the 1990s. They completely stopped development around 2000 something when the airborne program laser program was stopped. So moving on to systems, so these were lasers. Now, what is needed from a laser-based interception system? So you need to focus a high-power laser beam on a target, which can be rockets, missiles, whatever. You have to heat the target and damage the target or detonate its explosive. So this requires high power density on a target. That means high power, small spot on a target for a few seconds. So, and this in turn requires a very accurate tracking system with angular resolution of microradians. That's not easy. And you need also to overcome atmospheric effects, aberrations, lensing, turbulence, etc. So bottom line, it's a very complex problem. In the early 70s, I'd say to 90s, 2000, many technological prototypes were developed, but stayed in the prototype range. So this included mainly gas lasers and chemical lasers. No system in the US, I think, went into operational service, and all projects were eventually stopped in terms of chemical lasers. The powers were relatively low, 100 kilowatt. I think this should be one. Most prototypes were low, but there was one prototype which was 1 megawatt, I think, in the 1980s. So this is not accurate here. And the SDI project, which I mentioned earlier, which were conceptualized in the 1980s, actually they didn't, after the USSR broke, they didn't move on. But the claim is that this, at least concepts, intercepted the USSR because then after the 1990s, it couldn't keep up with this financial high-cost projects. Here I show some leading chemical-based laser interceptors. On the left, you can see the Nautilus system. It's a US-Israeli project, and it successfully shot down rockets and artillery shells. On the right here, you can see the airborne laser, which was a chemical laser that was put on a Boeing. And this was a very, very costly project, and eventually it was canceled in 2010 because of the high costs. Here you can see another laser, or let's say a test bed for a laser. It's called Miracle, mid-infrared advanced chemical laser. And it did some experiments with over a megawatt in 1980. So this is a very, very powerful laser. And this is a hardest concept, I'd say, if not the woman of a chemical laser they proposed to develop. But this did not, it's called the Skyguard, this did not go forward in the US. Leading solid-state laser interceptors, you can see here, you can see here on the left, you can see the 100 kilowatt systems. It's called JHP SSL. This is the Nautilus system. This is not the Nautilus, sorry. This is the what I talked before of combining 5 channels, solid-state channels. And here you can see an example of the LAWS systems, which has fiber lasers and combined on the target. So I think this was demonstrated with 30 kilowatt, but here it says they aim for 100 kilowatts. So I don't know exactly the numbers here. Here you can see a small buggy, I would say, of Raytheon. This was exposed 2 years ago, and I think it has 10 kilowatts, 1 micron fiber laser. It's meant for anti-drones. And this is the Rafael system, which is called Drone Dome. And there are several fiber laser systems being developed now in the US, currently 60 kilowatt, but 150 and 300 kilowatt are under development. All kinds of entities there developing these systems. So now I'll move on to the light blade or Lavor Cinderella story, I call it. And these are the founders, Udi Benami, who's a colleague of mine from industry. Rami Aroni and myself started this thing together with the police, mainly the border police and the IMOD. It started in April 2018 when the first fire kites and balloons were flown from Gaza in the south to Israel, with causing a lot of fires and damage to fields in the south. So how the story began, the idea of shooting down kites and balloons, actually, Udi, my colleague, came to me, told me, let's do something about it. I told him, well, the big industries are taking care of it. So let's not do double booking and not waste our time on it. But then as we saw that nothing is being done over 1, 2, 3 months, we got together with Major General Yaakov Shabtai, which is currently the head of the police, and we did some brainstorming, filed a patent, and we built the first manual prototype of Lavor 1 in 8 days. So this was really something that was very fast. So we call this the coffin. You can see here a coffin-like system, and it sat on a table here, as you can see. And here, after we, to prove the concept, we just aimed the laser at this balloon here, and I'll show you a short movie. And you can see when the laser starts, the first balloon knocks out, and as the second balloon passes through the beam, so the other balloon also is burned. So then we put this system on a tripod, and we did some manual tracking. We succeeded to track all kinds of balloons which were carried out by drones and stuff. And then we tried to go down to the Gaza border. So it's me and my student, but then the IMOD said, well, you first have to pass some tests in the IDF facility. So we did some testing and we were successful. They said it's a very good lab prototype, so it cannot be tested in the field, but it did the job. So we proved the concept, gained some attention. So we founded a company called Opti Defense, which Ben-Gurion is part of it. We acquired funding and we developed a larger and automated Lavor 2 system. This development was half a year, very short time scale. So this is the Lavor 2 systems. It's an interceptor. You can see it's mobile. It's fully automatic. It has tracking. It has special focusing and day and night operation, a remote control station. It's low cost compared to the US systems, and it was deployed successfully in Gaza. I'll talk about it in a minute. But we aim mainly at homeland security applications, and that's why we try to make it very, I'd say, cost effective. This system of ours is special because of the minimal danger footprint, because of we're using an eye-safe laser, and we have special focusing. So the distance after the target, which is safe, is rather short, and it's very important for operation in dense populated areas. So this is some pictures of how we built the prototype. This is first experiments in July 2019 in the field, but they were not successful. The tracking system didn't work yet well enough, so we went back and did some development again. This shows a movie where we first shot down a balloon at 1 kilometer. I'll just show you the movie. So this was the first knockdown of the balloon. Then in November 2019, we went again for field testing, and this is a short movie I can show you that shows some of the results. Same thing with the And so in December 2019, the system was publicly exposed by the border police. In February 2020, in August, we did some experiments on the Gaza border. So this made a lot of buzz in the press, as you can see here. And in August 2020, we had some very successful operation, and we managed to shoot down a lot of balloons, and they landed in the Gaza Strip. The payload landed in the Gaza Strip. So this was very nice. So what's next? The Laiser system has a limited range. So we're currently trying to upgrade the system for longer distances, and mainly to develop increased anti-drone capabilities, i.e. longer range, shorter times. So this is where we are, and I thank you for your attention.
Well, thank you very much. Thank you very much, Ami, for the presentation. I might say that this is an outstanding example for joining an acute need for confronting threats on natural scenery and the well-being of the civilian population, together with academic research and the real-time application of laser technology into a tight scheduled project. And I would like to ask you if there is any intent to multiply the Laiser system or its next generation, maybe.
So basically, we offered to, we can manufacture several more systems, and definitely there is need for more coverage in order to protect the southern border of Israel from balloons. But this is a decision that has to be taken by the Israeli Ministry of Defense, and they're thinking about it, I think. They have their own priorities, and it's and they have to take the decision. We can clearly do it, but as a company, as a say a financial entity, we are really we would like to defend the southern border, but other than that, the opportunities lay in the anti-drone scenarios. So we're now currently trying to develop an upgraded system that can confront these threats. So and shooting down drones is a different scenario than balloons, because you have to have some dwell time on the target, and that requires all kinds of better tracking and all kinds of other stuff. So this is where we are currently.
Another question, comparing to other existent anti-drone systems, how do you appreciate the laser-based anti-drone systems? Are they more effective or effective the same amount? What is your opinion?
So many companies abroad and also in Israel have their, or claim to have, their anti-drone systems. I think the general solution for anti-drone systems consists of several layers. So the RF jamming and the GPS jamming and all that, and the cyber jamming or cyber takeover are these are soft kill systems, and they're definitely in place, and they're already sold across the world, even by Israeli companies. The hard kill effectors are also being developed, and Rafael claims to have a system. And also in the US, there are systems, but these systems are not eye safe, and the danger zone, they pose great limitations on air forces and air control and so and such, and that is indeed an obstacle in terms of regulation. So we aim to our product is aimed to go to the homeland security applications in dense populated area. I mean, defending airports, strategic places, and there's a need for eye safety, and I think that distinguishes all the other competing systems than our system, and because other than that, there are high power system, much higher systems than ours.
Thank you. And we have another two questions from the audience. I tried to put them together. The question is, what is the maximum distance that the LAVOR system can operate, and how much power is it in the beam?
So I'm not allowed to expose these parameters, but I can say against balloons, it's above 1 kilometer, and below, let's say, 10 kilometers, and the power is in the kilowatts or kilowatts regime. So I'm not allowed to say it exactly.
So thank you very much, Ami, for the very interesting presentation. And that brings us to the next presentation. One of the questions was the question of Hervé Moissan. And Dr. Hervé Moissan is the head of research and development on laser diodes at Lumibird. Hervé Moissan holds hello, Hervé.
Hi, Alex. I'm sorry, but I'm Tal. I'm from Event Place. We are the production company. I just wanted to say for 1 minute, because I know a lot of the people are experienced in the last hour some difficulties to connect to the live stream. So first of all, I just wanted to take responsibility and say that we did all of our best, and now we're back on live after a worldwide problem in technology. So I know AEAI is part of the technology on the worldwide system to create good imaging and photonics, but as you can see, CDN is not our as you can see, there is a big outage worldwide, and we tried to come back to the live stream, and we managed to do it. So first of all, the recording will be up I'm sorry, as soon as we finish this session, the recording will be back up. And of course, we're back on now live. So if your colleagues or teammates are came out because of the 20 minutes of outage that we had, you can please send them information about coming back to us and come to see all of the great presentations that you guys had. We did our best. You know, live events are all about what you do when something gets wrong. So we did our best to come back, and I'm thankful for all of you presenters as well to come back to the live session. And I wish for you all a great session to come back to.
Thank you, Tal. Thank
There
you,
you
Tal. Now we will proceed to our next presentation of Dr. Hervé Moissan, that is head of the research and development on laser diodes at Lumibird. Hervé Moissan holds a PhD in optics and optoelectronics from the Polytechnic Institute of Grenoble and a master degree in physics from École Nationale Supérieure de Physique de Grenoble. He was priorly granted a master degree in physics from the Université de Bretagne Occidentale at Brest, France. He has been working for 25 years in the field of optoelectronics and especially high-power laser diodes manufacturing and research and development, covering all stages of elaboration, from the epitaxy to the diode processing, assembly, and testing, including qualification and reliability for space programs. He is now the head of research and development on laser diodes at Lumibird. Hervé will talk about compact laser sources for LiDAR, diodes, and fiber lasers. Hervé, please begin your presentation. You are most invited to do it.
Welcome to this talk dedicated to laser source for LiDAR by Lumibird. I am pleased to meet you. I am Hervé Moissan, Head of Research and Development in laser diode activity at Quantel Technology. Lumibird is made of different companies covering the two business series of photonics and medical. Photonics cover every laser technology, each one supported by dedicated companies: Quantel Laser, Curbsys, Sensup, Allophotonics. Quantel Medical provides the instrumentation for the treatment of eye conditions, including laser and ultrasound technology. Lumibird is born in 2018 from the merger of Quantel and Curbsys, which have been two key players in photonic industry since the beginning. Back to 1970 for Quantel in solid-state lasers, and 1997 for Curbsys fiber lasers. Main part of the Lumibird growth is driven by the acquisition of companies in the core businesses of photonics and medical. The most recent acquisition being LX, former main competitor of Quantel Medical, gives to Lumibird a leading position now in the instrumentation for the treatment of eye conditions. Lumibird has more than 800 employees throughout the world today and is established in 4 countries. Each of the 9 sites has its own resources in manufacturing and resource in research and development. Users of the Lumibird products are from different sectors: industrial, scientific, defense, automotive, energy, and medical. A constant attentiveness of the market's needs keeps Lumibird ahead of the technical trend in photonics especially. Let's start by the solid-state laser offer by Lumibird. These are mainly based on neodymium sources. Both pumping technologies are offered: flash lamp pumping, which is affordable but short-lived, and diode laser pumping, more reliable. This page gives an overview of the various products designed for specific usage: scientific, defense, spatial, medical, The lineup covers a very wide range of optical energy, going from 10 millijoules up to nearly 2 joules, depending on the model provided. For the diode laser lineup, the core product is a diode laser stack, which is used for the optical pumping of the solid-state laser made by Quanta, or for external use, external customers. Quantel is able to offer more than 1,000 declinations of the QCW laser diode stack, tailored to very specific needs in size, in power, or in wavelengths. The wavelengths can cover the range from visible, 635 nanometers, to the near infrared, 1100 nanometers. Thanks to the stacking of the multiple laser diode bars, 1 centimeter long, we can reach peak power up to 10 kilowatts by simply and seamlessly add up powers from the single laser diode bar. This core technology provides a basis for various derived products, including fiber-coupled diode modules, short pulse illuminators, the high-end products being the pumping modules. Fiber lasers and amplifiers in the continuous or pulse modes are available in a wide wavelength range from UV to 2 micron, with a wide variety of applications, including LiDAR. Some of those lasers are also used in medical application, especially ophthalmology. This page covers some of the most prominent products from fiber lasers and amplifiers, including pulsed green fiber lasers, pulsed erbium fiber lasers, or frequency-converted ytterbium dot fiber lasers from 520 to 590 nanometers. Keopsis also provides critical components entering the laser, the fiber lasers, or amplifier. These components are all manufactured at Lumibird. Let's have now an overview of the different LiDAR technology that Lumibird offers right now. We have the flash LiDAR, which offers a whole thing lit up at once using a diode laser. Then we have a time of flight design, which requires short pulse laser, and from round-trip traveling delay can be derived the distance to the object. And finally, we have the frequency-modulated continuous wave, or FMCW, that relies on the analysis of interference pattern between the forward and backward return beams. For the pulse erbium fiber laser products that can be used in a time-of-flight LiDAR, we can provide a typical operating wavelength of 1550 nanometers at average output power up to 3 watts in pulses of 40 microjoules energy over a large pulse duration from 0.5 nanoseconds to 10 nanoseconds. The peak power can be reached up to 6 kilowatts. The pulse repetition frequency can go up to 5 megahertz, and we can provide the design and the product within a random or linear optical polarization with, in any way, an output beam which is diffraction limited. And of course, a wide operating temperature can be reached from -35 up to 65 Celsius degrees. Current development tasks are ongoing to enlarge this operating temperature up to 105 Celsius degrees and down to -40 Celsius degrees. For the FMCW application, we do not provide the source laser source yet, but we do provide the amplification modules. This is the CEFAC-PBHB design, which offers some products built on fiber amplifiers emitting at 1550 nanometers up to 5 watts average power. We can get 1 and 2 outputs, it depends, and we can adapt the size of the box, of the packaging, to the required power of the customer or the application. The laser diode technology at Lumibird provides the following benefits. We have the capacity, because the laser diode device or modules can be at least 10 times smaller than the solid-state laser counterparts. We can reach ruggedness and reliability thanks to CTE match material, which provides the benefits of having assembly resistant to vibration, thermal, and mechanical shocks. Thanks to the hard soldering technology which is set up on our products, we can ensure reliability on the laser diodes. This product is light in weight, only ounces. The efficiency can reach up to 70% with the product taken alone, or 30% at a wall plug. We can provide a wide range of output parameters, up to multi-kilowatts in optical power, in peak power, and the wavelength emissions can cover the near and SWIR, and also the visible range down to the red. The pulse width covers from the nanoseconds to the milliseconds range, even in CW. We can also provide capabilities in beam engineering. The pulse diode laser source can be provided for the flash Laiser, for example. This is the best features of this kind of device. And we draw the key features which are shown here. So the laser diode bar stack technology can be integrated directly on the driver board, which allows to reduce the pulse width, electrical pulse width, down to 3 nanoseconds. And the typical pulse width range can go from 3 nanoseconds to 200 nanoseconds on this design. The shorter the pulse, the higher the peak power. And we can draw benefits from a teeny footprint also. And the operating temperature range can go from -35 Celsius degrees up to 85 Celsius degrees. We can also provide the possibility to collimate the beam, which makes possible some engineering of the beam shape for specific application. Here is an overview of the available emission wavelengths provided with the diode laser products. We can cover on the 635 up to 1550 with various slope efficiency, with a maximum of 135 watt per amps for the 808 material, but still with a very high efficiency, conversion efficiency, up to 74%. The voltage is still low, larger than 1 volt and not much higher than 2 volts for the lower wavelengths products. We have to take into account some limitation in operation. In optical power, maximum optical power can be limited in certain circumstances and depending on the wavelengths, limited by 2 factors, either the COD, so catastrophic optical damage in the near, or either thermal effects in the visible or in the SWIR. Here are some samples of the illuminators line up on the near and SWIR wavelength ranges, actually. The pulse width, the pulse energy available scales up with the number of bars integrated onto the illuminator board, from few microjoules on the very short pulse region, less than 3 nanoseconds, up to the millijoule range for large stacks of up to 10 bars operated on 80 nanoseconds pulse duration at wavelengths 905 nanometer. In the near region, thanks to the triple junction technology implemented on the bars, record high energy can be achieved. In the SWIR, here at 1370 nanometers, We have recently demonstrated millijoule operation on stack of single junction bars. The drivers are designed to provide the specific pulse duration from nanoseconds to 100 nanoseconds. The dimensions of the devices are mostly related to the heat load and thus the average power and the pulse repetition rates. We do provide the full thermal solution fitted to the system if the cooling is required. And finally, on the beam geometry, if the beam geometry requires, fast axis collimation can be also provided. Here is an example which shows the recent performance achieved at 1370 on the illuminators shown in the inset. We achieve a linear scale-up of the output energy with a number of bars in a typical spectral characteristic, which is also shown with a peak wavelength at 1370 and a full width at half maximum of 20 nanometer. As a conclusion, Lumibirds offer a wide range of laser sources covering every LiDAR application in time-of-flight mode or FMCW mode using fiber lasers and amplifiers, or also in flash LiDAR using diode laser. Our motto is to provide higher performances and optimize design for a lower cost. We are fully dedicated to always provide an answer for customer needs taken from our various products lines up and with our customization capability. Thank you very much for your attention and for your time, and please do not hesitate to contact us for any commercial information. Please take note from the following email address.
Thank you, Hervé, for sharing with us the review of the impressive span of products of Lumibird. The ship shown in the last part of your presentation is also of some interest. But I would like to ask you about Lumibird's technology. Do you have any intentions to also explore the sub-nano range of pulse width? And are there any interesting applications in this range for Lumibird products?
Thank you very much. Regarding the pulse width range of our products, actually, we are covering, as you have seen in the presentation, from the nanoseconds range up to the milliseconds or even CW considerations. We do not offer much narrower pulse widths regarding our different options, at least in the fiber lasers or diode lasers options or solutions. I would not express my opinion about the solid-state laser, which is also a big part of our offer. But I think we can find some useful information on our website. Sorry for not being able to answer right now, but I think we can check it right now and give some additional information if you need. So far, I'm not very easy in this specific solid-state laser technology so far. I guess we are probably in the range of slightly higher in the solid state in the picoseconds pulse width range, very probably, but to be confirmed.
Thank you. In your presentation, you also mentioned that Lumibird has also some products and applications for space. Can you refer to some of these applications?
Yes, of course. For the diode laser products, for example, the ones that I'm currently managing the R&D effort, we had collaboration, historical collaboration with most of the prominent spatial agency around the world. So we've been working with CNES, ESA, European Space Agency, NASA. And as an example, we have our laser diodes that are used for optically pump the laser mounted on the robot Perseverance on Mars currently. And priorly to that, we were part also of the former missions and sent out to Mars in 2012. And we have also diodes in the same kind of apparatus and instrumentation used to carry out some leaps and mineralogical analyses on the planet.
Thank you. A question from the audience. Do you use also CW lasers operating at more than 85 Celsius degrees in your products?
So there are many questions, it's the same question. So if we talk about the diode laser technology, the CW products are currently used in the range of up to 60 Celsius degrees. So it's only for the laser diode options. If we are considering some new development we have launched within the last year regarding the pump single diode modules used for our fiber laser technology platform. So we are able to provide up to 85 Celsius degrees in the form of 940 nanometers laser diode, 10 watts typical. Fibered coupled into fiber modules, so hermetic also, it's our UCH device product. We plan to develop current effort in R&D are aimed at pushing this high limit up to 105 Celsius degrees to operate the laser diodes at the same wavelength range, 940 nanometers, but keeping the power the same. Roughly, we plan to achieve about 9 to 10 watts out from a 940 nanometers fiber coupled modules, hermetic, either 10 watts or probably also 30 watts, depending on what modules power we need to achieve.
Okay, thank you. I have to mention also that I had the chance to visit the beautiful city of Lannion in France. And it was really great. And I would like again to thank you for your presentation.
Thank you very much.
Thank you. And now we'll go to our next presenter, Dr. Zev Schiffer, that is a laser physicist at Elbit Systems, ELOP, the iStar division. And he's there for the last 20 years. He's involved in a variety of laser products with mid-IR iSafe OPO and other nonlinear converters. He's presently working on the development of both solid-state and fiber laser sources. Zev, a most talented and dear colleague of mine, will talk about compact high-brightness pulsed iSafe converter. Zev, please, the floor is yours.
Hello. Today, I would like to speak with you about something which we are currently have achieved in Elbit. It is a compact high brightness pulsed iSafe converter. To start with, we should talk about the motivation of such a product. Well, an iSafe sources are very suitable for applications such as range finding and homeland security illuminators, and also gated imaging and LiDAR. I guess some of you know these applications, basic principles of the basic technological principles of how these are done. So an OPO converter is usually in our applications is based on a Q-switch source, which is an ND-YAG laser, which is used as a pump source. The signals are produced by means of an oscillators, which in the case of a nonlinear process is called an optical chromatic oscillator, an OPO in short. And these oscillators generate a small amount of energy. So in order to get the final amount of energy, we amplify it by means of an OPA, which is an optical chromatic amplifier. So in the case of an iSafe source, we have three wavelengths, which one of them is, as we said, is the 106 ND-YAG pump source. It is the iSafe or signal signal wavelength which oscillates in the OPO, and there's an additional idler wavelength which is also a part of the nonlinear process, which is it is a byproduct. So if we look at the demands of such an airborne system or airborne OPO converter, what we would like to have is, first of all, high beam quality, because we're talking in most cases about applications from a distance, from a large distance. So in order to get a small pump spot, we would like to have a good beam quality, of course. And in order to get information or signal or something from the target, we'd like to have high energy. This is an airborne system, so we will also be glad to have small volume. Actually, this is a very heavy requirement of such a product. And since we consume our energy from the platform, which is, again, it has a small amount of energy, so we need to have also high efficiency, because we're taking our supply from some kind of a battery. So what we are heading on is upon a trade-off diagram, which apparently exists in any product, but especially it exists in an airborne iSafe source. So what we see here is three features, which for some reason we can get all of them. As you see at the center of the diagram, you see the dreamland, what we call the dreamland. It is the overlapping zone of all these three requirements or features. But regretfully, what we know is that usually when we want to have them all, we can't. We can choose two, but we need to give up the third. For instance, if we would like to have high beam quality and high energy, we need to give up the volume. And if we would like to have high energy and small volume, then we need to give up the high beam quality and so on. This is explained very simply by the well-known connection between beam quality and the Fresnel number. We see that the beam product parameter, the BPP in short, is related to the area of the aperture of the oscillator, and it should be divided. It is linearly proportional to the area, and it is divided by the length of the cavity times the optical power of the thermal load, or any other optical power which is inside the cavity. But the problem is that if we need to have high energy, this means that the intensity, which is the quotient between the pump energy and the area of the aperture, or the area of the pump beam, we see that in order to get a good beam product parameter, we need to have high intensity. But this high intensity at time is going to jeopardize our oscillator, because at the end we have some finite laser damage threshold, and when we are passing it, we're going to get laser damage to the first of all to the nonlinear crystal, and then to the whole cavity. So what we see here is that from very simple principles, we get a contradiction between good beam product parameter and beam intensity, or beam energy. So this is something which is classical to all oscillators, but in the case of an OPO, of a nonlinear iSafe converter, we're going to have even more problems, because in a regular oscillation process of a nonlinear converter, what we see is that the pump pulse, this is time, this is pump pulse. What we see is that in some delay, we're going to get a signal, which is the eye-safe desirable signal, and also an idler. This signal is going to have good beam quality as long we take care that the oscillation process does not generate some undesirable amount of other wavelength, which is something we can expect in a nonlinear process, because as we know, all three wavelengths are interrelated in the nonlinear process. So if we have a considerable amount of signal and idler, we're going to have a back conversion process, which means the energy of the signal and the idler generate an energy of the pump. So we're going to have a degradation of the energy of the BPP, of the beam product, due to nonlinear process. So I guess what everybody would think now is that maybe we should now split and make an OPO and an OPA. OPO is a low energy and maybe a small Fresnel number. So at the end, we're going to get small energy. And then with this large pump area, we can pump a nonlinear crystal and get a considerable amount of energy with good beam product, and not validating our principle of trying to get away from nonlinear processes, undesirable nonlinear processes. But it comes about that when we try to pump a nonlinear crystal as an OPA, what happens is something which is in analogy with the ASC, which is an amplified spontaneous emission. We have also an OPG process in nonlinear processes, which is an optical parametric gain, something which we can expect to happen when we don't have a good signal to be amplified, but it is something which is spontaneously happens along the crystal. So we can get a large amount of energy, but with very poor beam quality. What we need to have something which is called synchronization. Synchronization is when we have a signal which overlaps completely with the pump. So if there's a large amount of pump which happens and the signal somehow it succeeds in overlapping in a very good manner the pump pulse, we're going to have a good beam quality at the end of the amplifier, but also with high beam energy. But this is not the case when we usually use a low power or low energy oscillator, because what happens usually is that the OPA sees a lot of energy while the signal has a large delay. So the OPO signal comes, but it doesn't overlap the signal which is generated spontaneously in the amplifier. So what happens at the end is that we're going to get a contradiction. If we try to have high beam quality and high energy, so we need synchronization, and we're going to have a large volume and a problem of flow of. So we're going to get a contradiction. If you want to have small volume and high beam quality, then we're going to have to avoid optical damage. We're going to have low energy. So if we want to have small volume and high energy, we're going to have small poor beam quality due to all parasitic processes. So what we came up with is the next idea. So what we do, we're going to split the pump energy and manage the process. So by having a large pump energy, but small amount of energy split into the OPO, which is small, with small aperture and small energy. So it is synchronized because the signal starts right away. with low energy, but with good beam product parameter, we are able to take this signal and feed it into a stage, an OPA stage, optical parametric amplification stage, but with a very careful splitting and management of the pump energy, we're able to take care of the fact that we're always away from nonlinear processes. By taking away the idler and putting only the signal and the pump, we're going to have a very good beam parameter product at the end of this first stage with higher energy. Then again, we repeat the process by dumping away the idler and synchronizing the pump and the signal into a second amplification stage, and then having an output signal which has high energy and also very good beam product parameter. So what we have here is a process which fulfills all our demands. So as you can see, the process, along the process, we can have very good amplification and still keeping, by choosing the correct combination of pump split and signal and idler management along the process, we can keep all along the process a very good beam quality while elevating the amount of energy in a very stable and good manner. Also, in addition to the former parts, the higher energy and excellent beam product parameter, it is also the thing here is that we can have a very compact design with a good efficiency, which is again a very important feature for such a product. So at the end, what we summarize with is that we have a compact oscillator and amplification design, which is done by management of all the amplification stages, so we don't have any degradation of along the process, no beam product degradation. This design also have a potential for upscaling with the same design. It is efficient and with a very good beam quality for such an airborne purposes. So thank you, and I'm ready for your questions. Bye-bye.
Well, thank you, Zev, for sharing with us the principles of designing a high brightness iSave OPO converter. I would like to ask you what distinguishes the design concept of such a device planned to be integrated in an airborne platform from other products that might be used for ground platforms, for example?
Well, generally, what you would expect from a ground-based transmitter is the ability to be very transportable. I mean, something which is small can be supplied around a large amount of troops and so on. So product should be small, maybe lightweight, and all the parts that we usually call, I mean, small weight, small amount of volume, and small amount of energy requirements. So this is the main difference between the products. So maybe if we can land the design, which is basically it was meant for airborne transmitters. If we land it to the land, take it to the ground applications, it will be expressed as a smaller and cheaper product related to the classical OPO converters.
Thank you. And when talking about scale-up potential, what did you actually mean? Are you talking about scaling up energy or maybe something else?
Well, this design, it enables, without getting into too much into details, it is understandable that at the end, if you elevate the amount of energy and the amount of and you improve the beam quality, then the applications could be done from much larger distances. So this design, basically, it should enable multiplying or even tripling the amount of energy without damaging the beam quality. So the ability to control an area by using one aircraft, of course, it multiplies with no considerable, no significant elevation of volume or price. So this is the main the main ability of this product. It enables scaling up the energy and keeping the beam quality.
Well, thank you very much, Zev. The presentation was great. Thank you again. And we will go to our last but not least presenter for today. Due to the technical challenges that we faced during our broadcast, we'll have to continue a bit into the break between sessions. Sorry about that. You are invited to stay with us for the last presentation, though. And this presentation is a presentation of Vladimir Davidenko, head of photonics at Scantinel Photonics. Vladimir graduated in 1981 as theoretical physicist by Tartu State University in Estonia. Then he was a scientist in different laser development projects in the Institute for Solid-State Physics of Estonian Academy of Science. And since 1989, he was a Research and Development Senior Director in Small Enterprise of Estonian Academy of Science in the field of development and fabrication of laser spectrometers. Then he was vice president of laser systems in Limo in Dortmund, Germany. And afterwards, he worked on micro-optic components as a development manager. These components are used for optical column of wafer, advanced semiconductor materials lithography, steppers. And it was at Zeiss at Oberkochen in Germany. And since 2020 up to now, he's the head of photonics at Scantinel Photonics, spin out of Zeiss, developing integrated FMCW LiDAR. Vladimir will talk about massive parallelized frequency modulated continuous wave, FMCW, integrated LiDAR. Vladimir, you're invited to make your presentation. The floor is yours.
Ladies and gentlemen, allow me to introduce myself. My name is Vladimir Davidenko. I am 40 years experienced laser and optics specialist working for Scantinel Photonics in a position of architect of a photonic engine of the integrated LiDAR. Today I will talk about massive parallelized FMCW integrated LiDAR, which is a product we are developing in Scantinel. Scantinel is a spin-off Zeiss Corporation, known as medium-sized optical company. Scantinel was backed up by Zeiss business unit SMT, known as exclusive supplier of optical column for ASML wafer steppers. Key team members of our company come from SMT, where we spent the time by developing optical and metrology technologies used by semiconductor industry for CMOS chips fabrication. One of successful ZEISS SMT metrology projects results has become a technological basis for a new company, which was launched just before Christmas 2020 by 4 engineers and scientists, including myself. Scantinel positioned itself as fabless company. Our mission is to develop layout and technology of mass production of fully integrated Laiser chip or chipset to enable affordable 3D sensors for a wide range of applications. Our company selects excellent engineers and scientists having serious experience in photonic design, photonic packaging, laser technologies, optics, mechanics, and electronics, as well as data processing, reliability, and safety. To proceed with the development, we are using a network of development partners with whom we already have built the products. We partner with one of the pioneers in the commercial FMCW LiDAR technology development, Bridge Photonics, from Bozeman, Montana. Our photonic and CMOS process development partner is IMEC from Leuven in Belgium, known as leading development organization in the field of integrated electronic circuits and photonic integrated circuits technologies. We were inspired by capabilities of coherent measurement principle when it was applied to fast measurements. We have found that using coherent technology, one can develop quite sensitive and affordable sensors enabling huge number of applications, especially in robotics and autonomous driving. We at Scantinel Photonics are working for future 3D sensors technology development. The 3D sensors are a family of measurement devices providing data such as location, speed, reflectivity, chemical composition of material objects in the sensing cell. Such sensors will be needed to fully automate or even robotized with assistance of artificial intellect execution of a very broad spectrum of processes and services. Scantinel Photonics develops technology enabling mass-producible, integrated, frequency-modulated continuous wave scanning, light detection, and ranging system. Our main differentiation to other companies are CMOS compatibility of fabrication process of the photonic chip, CMOS technology enabling integrated narrow linewidth, fast tunable swap source, which is the key of entire technology. Advanced optical solution enabling solid-state scanning of the field of view, as well as massive parallelization of the measurement process, providing required pixel rate. Before I go into the details, giving you an insight into our technology, I would like shortly also explain why we do that. This is important for me to share with you our motivation. Society and media are intensively discussing a scenario of the next technological revolution. Digitalization of the economy, massive increase in the computational power and ability to manage huge information flux alone do not materialize into new abilities and do not generate new needs, which are required for economic growth. To be realized, all those digital abilities need to be connected to material world. Advanced interface is needed between digital world and material world to enable mankind an advance into the next technological level. This interface are sensors. FMCW LiDAR is most advanced and universal model of 3D sensors, allowing high precision operating in the distance ranges from few millimeters to many kilometers, providing Doppler image in the sensing sen as well as reflectivity and gas map in the sen. Nobel Prize winner Arthur Schawlow said, Never measure anything but frequency. Frequency is most reliable detectable physical magnitude. This instruction is the driver of the FMCW technology. The inset shows the schematics of the FMCW LiDAR, frequency modulated optical signal of the local oscillator, usually with linear modulated waveform, is sent to detector and to the sensing stand. The return signal, which contains information about location, speed, reflectivity, etc. of the sensed object, is mixed at detector with the local oscillator signal. Detected bit frequency between two coherent signals is proportional to the distance of the located object. Reliability of the measurement is based on the simplicity of the principle. The average of the bit frequencies produced by opposite chirp signs gives the range. The difference of the bit frequencies gives the velocity. Let me show the video demonstrating how the principle works in real life. Bright spot on the sheet of the assistant is a spot of the swap source with a triangle waveform of the frequency modulation as shown on the figure below. The object is located at about 100 meters from the sensor. Now, the object begins to move. I will repeat the demonstration one more time and give you additional explanations on that. This is a spot. This is the object. This is a peak which is detecting the location. Object moves, peak changes the location. So we measure simultaneously the range, which is shortened in this case because object is moved to us, and we measure simultaneously the speed of the object. Okay, we have seen how the measurement principle works. What about scanning? We may group currently applied scanning principles in three categories. Pure mechanical sensors, when mirrors, MEMS, or polygons are used to deliver the probe beam to different directions in the field of view. Phase array scanner, where phase control of the outcoming beam wavefront is used to deliver the probe beam into desirable direction. A new method, which we call OEA, relies on knowledge of optical system operating principles, namely if the location of the source placed on Fourier plane of the lens system is changed, the optical system will tilt outcoming beam. The mechanical scanners are usually bulk and due to the presence of moving parts are not reliable and also expensive. Phased arrays are fully solid-state scanner. However, phase array with high resolution require too much power, which is not affordable for civil applications. The OEA, what stands for Optical Enhanced Array, it is somehow a mixture of the phase array and mechanical scanner. The probe beam is created by source numerical aperture and focal distance of the collimator. The beam direction is defined by location of the source on Fourier plane of the collimator. The OEA consists of photonic chip having switchable output apertures what we call sources, and collimator having the photonic integrated circuit with those sources in its Fourier plane. Nothing is moved during the scanning process, but the electronic signal switches the aperture in the Fourier plane of the collimator. On the next slide, I show how unidimensional scanning OEA is designed. And in that case, of course, we need to have an additional mirror to provide a two-dimensional scan. On the left side, the 3D model of 1D scanner is shown. As I already mentioned, the scanning principle is fully solid state. Additionally, one recognizes very fast that the OEA that is not only a scanning principle, but also a key for massive parallelization of the measurement process, enabling ultra-fast pixel rate, which is limited only by data processing speed, but not by the scanner. On the right side, you see a picture of our OEA photonic integrated circuit fabricated by IMEC for us. The chip provides 256 switchable apertures and is used in our prototype. On the next slide, I will show you real measurements made in the real life, and please enjoy those pictures. The Laiser prototype, here is its picture, is located on the roof of the car. This particular device has 12 simultaneously operating FMCW channels. And now let us see how the picture looks like. So this is a picture taken during the real test. So you see here the real life picture, and also it's a 3D picture. This is somehow a new way of perception of the reality which we need to learn. So you see here also those lines, which are the lines crossing the road. So some lines do not cross, they somehow are in the air. So you see how look the cars which are coming from the right side, from the left side. I will repeat the video again, just you will see how the test looks like. Okay, just take time a little bit. Yeah, now. Yes. So you see here the car in front of us. It's the red one car. Now the white car is passing on the left side. So you see also a train which just passed on the left side. So now this black car. Okay. And now the complete scene will be moved shortly when we see how it works in the dynamics. And the color itself somehow represents here the ranges, of course. On this slide, I show the ability of a technology to show the really high definition 3D pictures. As I mentioned in the sensor which was used by the test in the previous slide, we have only 12 operating channels, but in principle we can go already today to higher number of simultaneously operated channels, and that is assumed that we are not limited in the number of the channels, because the limit currently is coming only by the data processing. So this needs to be improved further. But in case we have such a capability just to accept all the data which the LiDAR delivers, then we will see something like this. This is a 3D high definition image collected by the sensor, where the number of channels, acquiring channels, was emulated by the moving of the LiDAR in the vertical plane with additional scanner. But this is fully FMCW process, which is used to collect the data in the real world. It is not a simulation. Let's say not really an animation. Okay. In this slide, I want to summarize our fundamental advantages over the time-of-flight technology. In the society and also in the automotive community, it's always until now discussed what technology is better. So we stand for FMCW, as I mentioned before. So the reason for this is really a very high sensitivity of the measurement process, which allows to make a very compact device using CMOS technologies to fabricate high volumes. In the table, I took the criteria like a range measurement, velocity measurement, output power and eye safety, robustness, and the cost. So we today can easily go to 200, 300 meters with a target reflectivity 10%. And with a detection probability more than 90%. So this is why we are using very narrow linewidth laser and coherent detection principle. So additionally, what we do, that is we can optimize our photon information efficiency. So that means we are using only required number of photons to detect the location and the speed of our object in the field. Velocity measurement, as I mentioned, FMCW receives this data just as a collateral effect of the measurement process, and the time of flight cannot do that at all in the one pixel. In order to collect or deliver information on the velocity of the object, time of flight need to generate multiple measurements. So today we can go to 0.1 microsecond meter per second. That is our speed resolution, but we can improve it further with our systems. Output power. So we are using the system in the CW regime. So our output powers are in the range of 1 watt. In time of flight measurement, so the pulsed energy need to go, our power need to go to kilowatts in order to generate something usable. So with our system, we are easily in a class 1 devices. Coherent method of detection allow us to be very robust in terms of interference with sunlight, as well as with other LiDARs operating in the field of view. So in case of time of flight, you need to be very careful due to the interference with other LiDARs which are operating in your field of view. So, and the cost, as we are using technology which is CMOS compatible, so we are able to fabricate our LiDARs in high volumes with a very affordable price. So this is a summary what I gave you about our technology. Thank you very much for your attention, and I am open now for the questions.
Hello, Vladimir. Thank you very much for your presentation.
Thank you also for the opportunity to present at this event, and it was a great pleasure and honor for me.
It's great having you here. I would like to ask you, what are the main drivers for optimizing the size and the resolution of the OEA, the optical enhanced array?
The size is limited by the, if you mean just the size of the aperture, which indirectly also translate into the resolution. The size is limited only by the fabrication of the waveguides in the particular platform. Let's say if we are speaking about SOI, that could be in the range of a couple microns, which can give you really a huge number of output apertures and will translate into the resolution. So enhancement of the resolution, that is resolution that's just a number of your sources of your apertures, what you have. So in that case, as you understood, we have also so-called collimator or optical heat, and the optical heat field so is limited the size of the aperture of our photonic chip, and indirectly again the resolution. So improvement on the optical design, further extension of this field will gain the number of the sources and also the resolution.
Thank you very much, Vladimir. Thank you again for the most interesting presentation. Maybe we can also talk about this intriguing concept afterwards. I would like to do so afterwards. And this actually concludes our session for today. I would like to thank our presenters and to you, dear audience, for participating in the Laiser and Laiser session. And finally, I would like to thank Nufar Sharan and Shlomo Glazer for organizing, together with many others, of course, such a great conference, letting the photonics community meet again. Goodbye, stay safe, and have a nice evening session. Thank you.